All right, let's get right into it. If you work with industrial sewing machines, you've seen this a million times. It looks like a simple, maybe a little annoying cleaning issue. But today, we're going to show you why that gunk building up in your bobbin case, it isn't just dirt, it's actually a sign of a critical engineering failure that's messing with your entire system.
Yeah? Look familiar? Of course it does. This mess of lint, thread bits, and grime is pretty much a daily sight. We've all been there. You pop open the hook, you see this, you probably sigh, and you grab a brush or some compressed air. You figure, hey, it's just part of the job. But what's really happening under all that fluff is way more serious.
So the big question is this really just a simple cleaning problem? Is the main goal just to make it look neat and tidy again? The answer is a hard no. In fact, thinking of this as just a hygiene issue is probably the single biggest mistake we make. And believe me, it's the root cause of so many of those mysterious quality problems that pop up down the line.
To really wrap our heads around what's going on, we have to completely rethink what a bobbin case actually is. It's not just some little metal cup that holds your bobbin. No, its real job is way more sophisticated than that.
Now, I want you to focus on this phrase right here, dynamic friction regulator. Just let that sink in for a second. This little part isn't just a part, it's a precision instrument. In fact, it's the most sensitive and precise one in the whole lockstitch system. Its purpose isn't just to hold something, it's to regulate.
So what does that actually mean? Well, its entire job is to use friction as a tool. It's engineered to apply a perfectly consistent, controlled amount of friction to the thread as it comes off the bobbin. And that controlled friction is what gives you stable, predictable bottom thread tension, kind of like the braking system on a race car. It has to be smooth, reliable, and predictable every single time.
And here we go. This is what it's supposed to look like. This is the ideal state. Just look at those smooth, polished surfaces. Every single curve, every angle is engineered for one thing and one thing only, to let that thread glide with a very specific, constant amount of resistance. This right here, this is your baseline for quality. This is what control looks like.
Okay, so what happens when that clean, controlled environment gets all gunked up? Well, it's not just one problem. It's a whole cascade of failures, a domino effect that ripples through the entire machine and messes with your final product in ways you might never even suspect. Let's break down exactly how this damage happens.
So the very first thing to go is your tension control. Instead of that smooth glide we just saw, the thread starts to stick and slip. It literally catches on a piece of debris, the tension spikes, and then it suddenly yanks free. This turns your nice, stable tension into a chaotic, pulsating mess. And what do you see on the fabric? Wavy, ugly seams and stitches that are all over the place. Now this is a big one. It's what I call the phantom timing problem, because it sends technicians on a total wild goose chase. That debris physically changes the path the thread takes. This delays the moment the thread loop expands for the hook to grab it. So get this, your machine's mechanical timing could be absolutely perfect, but you're getting a dynamic timing error caused by the gunk. It looks exactly like your timing is drifted, but no amount of wrenching on the machine will ever fix it. Take a good look at this number, 15 to 30%. That is a huge deal. That's how much strength your thread can lose just from being dragged through that contamination. I mean, that's a massive drop in seam integrity. And the reason for it is that the debris, well, it's not just soft, fluffy lint.
And this analogy is just perfect. That gunk is a nasty mix of fiber, sure, but also hardened, oxidized oil, tiny metal particles from wear and tear, and even melted residue from thread coatings. So as the thread is flying through there at incredible speeds, this abrasive paste is literally sanding it down, fraying it, and weakening every single stitch you make.
And the problem isn't just in the bobbin case. That contamination is part of a bigger system of buildup in the whole hook area. This contrast here is pretty stark, right? You can see that caked-on abrasive material all over the hook race, and it all starts in that one tiny, critical area of the bobbin case. Here's the worst part. This isn't just a static problem that sits there. Oh no, it is an active, self-destructive cycle. The contamination actually works to create more contamination, and it gets worse and worse at an accelerating rate.
So engineers have a fancy name for this, a thermotribological runaway. It sounds complicated, but it's really just a vicious cycle. Let's walk through it. It all starts with a little debris, which increases friction. As you can see, that friction generates heat in that tiny area. That heat then literally cooks the lubricating oil, degrading it and turning it into a hard, sticky sludge. And what does that sludge do? It traps even more debris, which, you guessed it, increases the friction even further. And the cycle just keeps going. It's a one-way street to total system failure.
This brings us to a very modern and kind of surprising problem. In a smart factory, you've got AI quality control systems looking for patterns and defects. But because this bobbin case issue creates totally random, unpredictable defects, the AI just gets confused. It might flag a great operator or a perfect roll of fabric because the real root cause, a loss of the machine's repeatability, is totally invisible to its algorithms.
And this table really shows why the problem is so easy to ignore. It's just deceptive. From the operator's point of view, hey, the machine still runs. You can even get some good stitches every now and then. A mechanic might come over and crank up the tension, and for a little while it might even seem to fix the problem. But the engineering reality is, the system is completely unstable. The process is out of control, and you're just putting a Band-Aid on a much, much deeper wound.
So, all of this demands a fundamental shift in our mindset. We have to stop thinking about this as simple cleaning and start thinking about it as active process control. This isn't janitorial work. This is hands-on engineering. And how fast can this all go wrong? Well, in high-end production, especially with modern synthetic fabrics and coated threads, you can get a measurable change in friction in just 3 hours. 3! That means if you're waiting until the end of a shift to clean, it's already way too late. Your process has already gone out of control.
And that's why we have to see this differently. This is not optional maintenance you do when you have a spare minute. It is a non-negotiable, absolute process control requirement. It's just as important as controlling your machine's speed or the temperature in the room. You must control the friction environment inside that bobbin case.
So when it all comes down to it, what's the real goal? It's not just to keep it clean. The true engineering goal is to keep the friction coefficient, that's what the Greek letter mu here stands for, to keep it constant. You are actively managing a critical variable in the physics of how a stitch is formed. That is the only path to a stable, repeatable, high-quality process.
Ultimately, everything we've talked about comes down to this single image. On the top, you have an uncontrolled system. You have unpredictable tension. You have damaged thread. You have random defects. You are in a state of failure. And on the bottom, you have a controlled system. You've got precision, stability, and quality. That's the real difference. That's the power of understanding the engineering truth.
So let's end with the single most important takeaway from all of this. If you remember one thing, make it this. A dirty bobbin case is not a hygiene problem, it is a dynamic tension control failure. So, the next time you look inside your machine, what are you going to see? Just some dirt that needs to be wiped away? Or a critical system that needs to be controlled?